Welcome to the Power Electronics class. Myself B. Veernarayana, Senior Assistant Professor, Department of Electrical and Electronics Engineering. We completed first 2 units. Now coming to the third unit, AC to AC voltage regulators and cycloconverters. AC to AC regulators and cycloconverters. At this end of the unit, student will be able to explain or analyze the operation of AC voltage controllers, and they are going to analyze the operation of cycloconverters. Coming to the contents present in this third unit, here we have 2 halves. First half covers AC to AC regulators and second half covers the cycloconverters. So if we go through this AC to AC regulators, here we have principle of phase angle control and on-off control, which are used to control the output voltage of AC voltage controllers, and single phase AC to AC regulator with R load and RL load for continuous and discontinuous conduction, transformer tap changing using anti-parallel thyristors. Single phase, this part covers the AC to AC regulators, and single phase bridge type step up cycloconverter with R load, single phase bridge type step down cycloconverter with R and RL loads, here continuous and discontinuous conduction mode. And next one, 3 phase to single phase or 3 phase to 3 phase cycloconverters. These are the contents present in the third unit. And coming to this first topic, single phase AC to AC regulators. Coming to the learning outcome, at this end of this lecture, student will be able to explain the principle of phase angle control and on-off control or integral cycle control, and learning outcome 2, explain the operation of single phase AC to AC regulator with R and RL loads. So here AC to AC regulators. So AC to AC regulators, the name itself, that AC voltage regulators or AC to AC voltage controllers are semiconductor based devices which are used to convert fixed alternating voltage to variable alternating voltage without change in the frequency. The AC to AC regulators or AC voltage controllers are semiconductor based devices, circuits, which converts fixed alternating voltage to variable alternating voltage without change in the frequency. Where we can use this variable AC means like speed control of the single phase or 3 phase AC motors, and tap changing applications, transformer tap changing applications, and lighting control, induction heating applications. You need to collect the variable AC. So before inventing these power semiconductor devices, if you want to collect that variable AC, simply we depends on auto transformers, variable reactors, tap changing transformers. These are used to provide the variable AC before inventing the power semiconductor devices. After inventing these power semiconductor devices, we will design one converter by using the thyristors and the triacs. We will design one converter which is used to convert the fixed alternating voltage into variable alternating voltage without change in the frequency. There are several advantages of these power semiconductor devices. So the size and cost of these semiconductor devices are very low, and smooth operation should be able to collect. Efficiency is very high. Okay, there are several advantages of these AC voltage controllers which are designed by using these power semiconductor devices. One of the main drawback or the major disadvantage of this AC voltage controller which is designed by the power semiconductor devices is it injects the harmonics into the source side or load voltage, especially when the output voltage is low. That is the major drawback of this AC voltage controller. However, there are several advantages of these AC to AC regulators over the conventional devices like trap changing transformers or auto transformers. So compared to that, these AC voltage controllers have several advantages. And these AC voltage controllers are adaptable for closed loop operation also. Here these AC voltage controllers are acceptable or adaptable for closed loop control system. There is one more advantage, and here we have high efficiency, flexibility in control, compact in size and less maintenance. These are the major advantages of thyristor or triac based AC voltage controllers. So here the main disadvantage of this AC voltage controller is the introduction of harmonics, objectional harmonics in the supply current and load voltage waveforms, especially when they are operated at reduced output voltage levels. This is a simple introduction to this AC voltage controllers. Before invention the power semiconductor devices, mainly we depends on auto transformers or tap changing transformers, magnetic amplifiers and saturable reactors, etc. are used to provide the variable AC. After inventing the power semiconductor devices, these devices are replaced by thyristorized or triac based AC voltage controllers. And coming to this, here there are two different types of control techniques. We said the AC to AC regulators or AC voltage controllers are used to convert fixed alternating voltage to variable alternating voltage without changing the frequency. So how you collect that variable frequency? Sorry, how you collect that variable voltage? So there are two different control techniques are possible to control the output voltage of AC voltage controller. Those are phase control or phase angle control, and second one on-off control or integral cycle control. On-off control or integral cycle control. If we go through this phase control, in phase control the thyristors are used as the switches to connect the load circuit to the source in each and every half cycle of the source voltage. Here in phase control, the thyristors are used as the switches to connect the load to the source for a part of every input cycle. For a part of every input cycle. That means the thyristor is switched on for a part of positive half cycle and similarly for the negative half cycle. So the load is connected to the source for every cycle of the source voltage. And by controlling the phase angle or firing angle or triggering angle, we are able to control the RMS output voltage in the AC voltage control. So to understand this phase angle control, here simply I go with single phase AC voltage controller with R load. Single phase AC voltage controller with R load. Like go through the here. So here this is simple representation of single phase half wave AC voltage controller with R load. The single phase half wave AC voltage controller is designed by considering the two semiconductor devices which are connected in anti-parallel between the source and the load. Here two switches, one is controllable device, here I am considering the thyristor, another one is the uncontrollable device, diode. If you connect one thyristor and one diode in anti-parallel to each other between the source and the load, then this is the simple circuit consisting of AC voltage controller, half wave AC voltage controller. So if we go through this half wave AC voltage controller, if we go through the phase angle control, see what happened here, this alternating this here, the source is alternating voltage. So what is the source voltage here? Simply we consider this like this source. So during the positive half cycle of the supply, T1 comes to the forward biasing mode, D1 is reverse bias. At omega t is equal to alpha, we provide the gate pulse to the T1. Then T1 comes to the on state and the source is transmitted to the load. So from this alpha, the source is transmitted to the load and the current flow through the circuit is like this. The current flow through the circuit is like this. So here, see here, you have some output voltage from alpha to pi. And output current, here I am taking the resistive load now. So output current is simply in phase with the voltage. So output current like this, and that magnitude should depends upon the resistance. And during the negative half cycle, this terminal is negative and this is positive. So corresponding that D1 comes to the on state. Why? Because we consider the ideal devices, and this lower is diode, which is uncontrollable device. So as long as cathode is made negative, then automatically the diode comes to the on state. So this negative cycle will transmit to the load here. And similarly, positive half cycle, if you provide the gate pulse to the T1, again T1 comes to the on state. So here in this phase control depends upon the firing angle. The thyristor conduction period can be changed. So if you go through this full wave AC voltage controller, later I will explain. If you go through this full wave AC voltage controller, here we use two SCRs. Hence why we provide the two gate pulses. This is for V1, T1, and this is for T2. So the positive half cycle is connected to the load and negative half cycle is connected to the load. That means if you go through the phase control, here what I mentioned here in the phase control, the load is connected to the source for a part of every input cycle. For a part of every input cycle. And in this phase control, by varying the alpha, we are able to control the output voltage. That is simply called the phase angle control, which is already discussed in rectifiers na second unit. So in that rectifiers also, those are called phase control converters. That means there we vary the firing angle, corresponding that we are able to control the output voltage. Coming to this second control technique, on-off control or integral cycle control. So in industry, in some applications, you need to maintain thermal time constant or mechanical time constant for the order of some seconds or some finite time period. You need to maintain the either thermal time constant or mechanical time constant. For example, if you want to maintain the mechanical time constant for the speed control drives, and if you need to maintain thermal time constant for the heating applications, then you need to provide the constant speed or you need to provide the constant voltage or constant power to that load. Then some finite time period, the load is continuously connects to the load. The load is continuously connects to the source, and some finite time period, the load maybe disconnects from the source. That means here, if you go through the integral cycle control or on-off control method, we will continuously, some number of cycles depends upon the load, we will continuously connect the load to the source for some finite time period, and for some finite time period, the load is disconnects from the source. That means that SCRs present in the circuit is continuously on for some time period and continuously off for some time period. Depends upon the way you are adding number of cycles, the load is connected to the source, and some finite time period the load is disconnected from the source. By on and off of this source connects to the load, we are able to control the output voltage. That type of control technique is called the integral cycle control or on-off control. The name itself, on-off. So in this, when we prefer the integral cycle control, means some special applications whenever you need to maintain either mechanical time constant or thermal time constant is order of the several seconds. If you want to maintain the constant, like speed control drives, if you want to maintain the mechanical time constant in speed control drives, or you maintain thermal time constant such as heating loads, for such applications almost no variation in the speed or temperature will be noticed. If control is achieved by connecting the source, some cycle to the load, and the source is disconnected from the load for some off cycles. So here how you can consider this on-off control, simply I will go this, see, observe here, we assume this one is the source, one cycle, second cycle, third cycle. Hence why here I am taking n is equals to 3, which is simply representation of number of on cycles. N is equals to 3, which is a simply representation of number of on cycles. And next two cycles, 1, 2, those are considered as the off period, which is represented by the m, which is the representation of number of off cycles. And next again n is equal to 3, 1, 2, 3. Next the load is disconnected from the source for the next two cycles. In this manner, if you on off periodically you maintain like this, we are able to control the output voltage. So here if we consider the number of on cycles, that means here first 3 cycles connects to the load and next 2 cycles the load is disconnected from the source. That type of control technique is called on-off control or integral cycle control or burst firing control. But in case of phase angle control, in each and every cycle we are able to connect the load to the source continuously by varying the firing angle. If you control the output voltage, that is simply called the phase angle control. So see here, I just want to provide this continuous pulses now. Hence why by default here the gate pulses are provides to the thyristors at omega t is equals to 0. See, at omega t is equal to 0, we provide the gate pulse to the T1. Hence why this positive half cycle will appear across the load. At omega t is equal to pi, we provide the gate pulse to the second thyristor. See here, this is the gate pulse to the second thyristor. Due to that negative pulse is available across the load. And again positive half cycle at 2 pi, we provide the gate pulse to the T1. So positive half cycle. If you have the negative source, then you need to provide the gate pulse to the second thyristor. So here, this one, positive, negative. After that, for completion of 2 cycles, we never provide the gate pulse. If you don't provide the gate pulse to the thyristors, those are continuously in the forward blocking mode, which are off state. Hence why here the output voltage is 0. And then next we provide the gate pulses corresponding that they comes to the on state. So let us assume, to understand this integral cycle control or on-off control, how you control the output voltage. Let consider n is equal to 3, which is the representation of number of on cycles, and m is equals to 2, which is the representation of number of off cycles. So here the RMS output voltage should be given by 1 by time period integral 0 to 2 pi Vm square sin square omega t d omega t for first on cycle plus integral 0 to pi Vm square sin square omega t d omega t for second on cycle, and so on, integral 0 to 2 pi Vm square V square sin square omega d omega t for nth on cycle. So if you have n on cycles and m off cycles, then the time period is simply given by n plus m into 2 pi m. N plus m into 2 pi. So the RMS output voltage can be written as Vrms is equals to, here first on cycle, second on cycle and nth on cycle. If we have n is considered as the number of on cycles now, then we will write n by 2 pi into n plus m integral, limitations are 0 to 2 pi V square m sin square omega t d omega t whole power 1 by 2. By simplifying this expression, what you are getting here, n into Vm square common out of integral, n into Vm square divided by 2 pi into n plus m na. Here sin square omega t is written as 1 minus cos 2 omega t by 2. So what you will write here, Vm square n divided by 2 pi into n plus m integral 0 to 2 pi. This sin square omega t is written as 1 minus cos 2 omega t d omega t. So by simplifying this, Vm square into n divided by 2 into 2 4 pi into n plus m integral 0 to pi 1 minus cos 2 omega t d omega. By simplifying this expression, you are getting Vrms is equals to Vm by root 2 into root of n by n plus m. This root of n by n plus m is simply considered as the k. So finally, Vrms is equals to Vs into root k. This Vm by root 2 is nothing but source voltage. So Vrms is equals to Vs into root k, where k is simply given by n plus m, which is the duty cycle of the AC voltage controller. Which is the duty cycle of the AC voltage controller. K is equals to n by n plus m, where n is the number of on cycles and m is the number of off cycles. And if you want to find out the RMS output current, IRMS is equals to Vrms by R. And similarly, power delivered to the load, Vrms into IRMS, which is simply given by either V square RMS by R. By simplifying this expression, we are getting K into Vs square by R. And here input volt ampere, which is given by Vs into RMS value of source current. Vs, RMS value of the source current is Vs into IRMS, which is given by Vs into Vrms by R. That is the input volt ampere. And if you want to find out the input power factor, this is the formula Vrms by Vs, very important one. For the competitive examination also, you are getting the question, he gives number of on cycles and number of off cycles of the AC voltage controller, then what is the input power factor? Very important formula. Input power factor is equals to root k in integral cycle control or on-off control method. And similarly, each thyristor conducts for 180 degrees. If we go through the integral cycle control, 0 to pi, T1 conducts, pi to 2 pi, T2 conducts. And again positive half cycle, whenever the positive half cycle will be available across the thyristors, T1 will be comes to the on state. Whenever the negative half cycle will be appears, then the T2 comes to the forward bias. If you provide the gate pulse, it comes to the on state. Especially if you go through the integral cycle control, the conduction period of each SCR is 180 degrees. So, as each thyristor conducts for 180 degrees, each cycle of n on cycles, the average value of the thyristor current is simply given by ITA is the thyristor average current. ITA is equals to 1 by 2 pi integral 0 to pi. Previously, if you want to find out the RMS output voltage, we consider 0 to 2 pi. But here thyristor average current, each thyristor conducts for 180 degrees, hence why that limitations are taken as 0 to pi. Im sin omega t d omega t for the first on cycle plus 1 by 2 pi integral 0 to pi Im sin omega t d omega t for the second on cycle and so on up to nth on cycle. Then if you have number of on cycles is n, then n by 2 pi into n plus m integral 0 to pi Im sin omega t d omega t. By simplifying this expression, you have got Im by pi into n by n plus m, which is k into Im by pi. K into Im by pi. That is the thyristor average current. Similarly, thyristor RMS value of thyristor current ITR is simply given by Im into root of k by 2. These are very important formulas. RMS value of thyristor current is Im into root of k by 2 and thyristor average current is simply given by k into Im by pi. Input power factor is equals to root k and RMS output voltage is Vs into root k. Very simple formulas. So this is the simple representation of on-off control or integral cycle control method. So first we go through this single phase AC voltage controller. Let me explain here. See here, this is single phase AC voltage controller And if you have one thyristor and one diode, this is simply called the single phase half wave AC voltage controller. If you go through the output voltage in AC voltage controller, half wave AC voltage controller, if you vary the firing angle, corresponding that the positive portion of the output voltage can be controlled. For example, if you choose alpha is equal to 0, then this total positive half cycle will be available across the load. If we choose alpha, some 60 degrees or 45 degrees, from this onwards you get in the output voltage. If you choose alpha 90, from here onwards, alpha 120, here onwards, you will get in the output voltage. Why? Because the T1 is controllable device. By varying the firing angle, we are able to vary the conduction period of the thyristor. Conducting period of the thyristor. Depends upon that firing angle, the positive portion of the output voltage can be controlled. But the negative portion, here we have diode, hence why irrespective of the firing angle, from pi to 2 pi, continuously you are getting the negative pulse. Hence why these half wave AC voltage controllers are not preferred for the practical applications. Why? Because there is some inequality in the output voltage of positive cycle and the negative half cycle. Due to this inequality, the harmonics must be injected into the source side. Hence why for the practical applications we never consider these half wave AC voltage controllers. Hence why most of the cases we go with the full wave AC voltage controller. The main drawback of the half wave AC voltage control is there is some inequality in the output voltage waveform of the positive half cycle and the negative half cycle. Depends upon the firing angle, we are able to control the positive portion of the pulse, but in the negative half cycle, by default, it has the diode, hence why pi to 2 pi continuous negative pulse will be available across the load. Due to the inequality, the harmonics must be generated into the source side. So to overcome the problems, practical applications mostly we go with the single phase full wave AC voltage controllers. So now we concentrate on single phase full wave AC voltage controller with R load first of all. So this one single phase full wave AC voltage controller with R load. That full wave AC voltage controller is designed by two controllable switches. Here we consider the two SCRs which are connected in anti-parallel to each other between the source and the load. Here simply the load is considered as the resistive load. So coming to this operation, during the positive half cycle of the supply, terminal A is positive and B is negative. Here during the positive half cycle of the source voltage, the terminal A is positive and B is negative. Corresponding that T1 comes to the forward biasing mode and T2 is in reverse biasing mode. Why? Because the anode of the T1 connects to the positive terminal and cathode of the T2 connects to the positive terminal. T1 comes to the forward biasing mode, T2 goes to the reverse biasing mode. At omega t is equals to alpha, we provide the gate pulse to the T1. At omega t is equals to alpha, we provide the gate pulse to the T1. So from alpha to pi, this portion of the source voltage is simply transmitted to the load. And the current flow through the circuit is given by source A plus T1 C R D B minus. In this way, the current will be flow through the circuit. And if you go through the current waveform, here we have the resistive load now. Hence why the output current is in phase with the voltage. And that magnitude should depends on resistance. I naught is equals to V naught by R. And this green line represents the voltage and this blue line represents the current. And from 0 to alpha, what is the state of 0 to alpha? What is the state of T1? Forward bias na. So this portion of the source voltage is available across the T1, 0 to alpha. You consider the practical diode or practical thyristor. There was some voltage drop 1 to 1.5 volts, depends upon the rating of the thyristor. The voltage drop across the thyristor during the on state can be varies from 1 to 1.5 volts. So from alpha to pi, this simply represents on state voltage drop. That means there was some positive voltage will be available across the thyristor during the on state, 1 to 1.5 volts, and remaining the source voltage is available across the load. Right. From alpha to pi, what is the state of T2? See here, T1 and T2 are in reverse bias to the each other, and whatever the voltage is available across the T1, the same amount of the voltage is available across the T2, but the polarity can be changed. That means if we have the positive voltage across the SCR, here the negative voltage will be available. So see here, from alpha to pi, what is the state of T1? On state. If T1 is in the on state, there was some on state voltage drop is available, this one. If T1 is in forward bias, what about the T2? Reverse bias. So the whatever the voltage is available across the T1, the same voltage is available, but the polarity can be changed. So 0 to alpha, we have some positive voltage across the T1. This magnitude will be available across the T2. Why? Because both the T1 and T2 are parallel. You know, the voltage across the parallel elements is same. So the same amount of the voltage is available across the T2, but the magnitude is same. Even though the magnitude is same, the polarity can be reversed. That means the mirror representation of this like this. So here 0 to alpha you have some negative voltage across the T2, and alpha to pi some negative voltage is available across the T2. So this is the operation for positive half cycle. See here, at omega t is equal to pi, output voltage is 0 and output current is 0. After that, the negative half cycle will be available across the thyristors. So T1 immediately goes to the off state. Now, during the negative half cycle of the source from pi to 2 pi, what happens here? During this negative half cycle, here terminal A is negative and terminal B is positive. Terminal A is negative and terminal B is positive. Now, due to this, T1 goes to the reverse biasing mode and T2 comes to the forward biasing mode. T1 anode gives to the negative terminal, T2 cathode gives to the negative terminal. So automatically T2 comes to the forward biasing mode and T1 goes to the reverse biasing mode. At omega t is equals to pi plus alpha, we provide the gate pulse to the second thyristor. Now what happens? From pi plus alpha to 2 pi, this negative source is available across the load. Hence why the output voltage simply follows the negative source voltage. That output voltage simply follows the negative voltage. And output current is in phase with the voltage. So from alpha to pi, T1 will be in the on state. Pi plus alpha to 2 pi, T2 in the on state. Right. If T2 is in the on state, what is the current flow through the circuit? Here B plus, D, R, C, T2, A minus and the source. If T1 is in the on state, the current flow through the circuit is like this from C to D. During the negative half cycle, if T2 comes to the on state, the current flow through the circuit from D to C. Whereas in rectifiers, always the current flows in one direction from top to bottom. But in case of this AC voltage controller, depends upon the switching condition of the thyristors, the current will be flows either from C to D or D to C, bidirectional current, which is alternating current. Hence here you are getting the positive pulse and the negative pulse like that. That is the output voltage and output current waveforms during the negative half cycle of the source voltage. Next, from pi to pi plus alpha, what is the state of T1? For reverse bias. See, pi to pi plus alpha, T1 reverse bias. Hence why that negative portion is available across the T1. Pi to pi plus alpha, what is the state of T2? Forward bias. So whatever the voltage available across the T1, the same voltage is available across the T2, but the polarity can be reversed. From pi plus alpha to 2 pi, what is the state of T2? On state. Hence why there was some on state voltage drop. That same voltage is available across the T1 also. And again 2 pi to 2 pi plus alpha, it comes to the forward bias. So the voltage across the thyristors will be gives like this, this one. And if you go through the current waveform, and here this is the voltage, this is the current. So these are the output voltage and current waveforms during the resistive load of AC voltage controller, and it's very very important, voltage across the thyristors. You confused here from alpha to pi. From alpha to pi, T1 is in the on state, no problem, there was some on state voltage drop. But across the T2 also, you have the voltage. Why? Because here both T1 and T2 are connected in parallel to the each other. So whatever the voltage available across the T1, the same voltage is available across the T2, but the polarity can be changed. If you have the positive voltage across the T1, by default negative voltage is available across the T2. If you have the positive voltage across the T2, by default negative voltage available across the T1. Magnitude should be same. If you have voltage across the T1 is 50 volts under forward biasing mode, the same 50 volts is available across the T2, but negative 50. See here, under forward biasing mode, this is the voltage across the T1. During this forward blocking of the T1, the same voltage available across the T2, but the polarity can be changed. The evaluator simply shows voltage across the thyristors. Yeah, here you have positive voltage, negative voltage, positive voltage drop, negative voltage drop, negative voltage, positive voltage. Yeah, you understand the concept, then he gives the full marks. So this is very, very important. If you understand where the voltage across the thyristors, then easily you understand the concept. So this is a simple representation of single phase full wave AC voltage controller with R load. And coming to the RMS output voltage here, RMS output voltage is simply given by VRMS is equals to 2 by 2 pi integral alpha to pi Vm square sin square omega t d omega t whole power 1 by 2. One by 2 pi m. So VRMS is equals to, take Vm square out of the root, 1 minus cos 2 omega t by 2 integral alpha to pi d omega t whole power 1 by 2. So by simplifying that expression, you are getting the RMS output voltage. Next one. Single phase full wave AC voltage controller with RL. It's very, very important. Single phase full wave AC voltage controller with RL load. Coming to the circuit diagram, coming to the voltage and current waveforms. So coming to this operation of single phase full wave AC voltage controller with RL load. You know, the single phase full wave AC voltage controller is constructed by using the two SCRs which are connected in anti-parallel to the each other between the source and the load. Here the load is considered as the combination of resistor and the inductor. That is a simple representation of the circuit. Coming to the operation, during the positive half cycle of the supply, terminal A is positive and B is negative. Terminal A is positive and B is negative. Corresponding that, T1 comes to the forward biasing mode, T2 is in reverse biasing mode. At omega t is equals to alpha, we provide the gate pulse to the T1. So, from alpha to pi, output voltage simply follows the source voltage. So, this portion of the source voltage is available across the load. Right. And due to the presence of the inductor, the current lags to the voltage by an angle phi, and there was some energy must be stored in the inductor. So, here that current waveform can be represented like this, and depends upon the value of the inductor, we are able to collect the continuous conduction mode and the discontinuous conduction mode. Let's go with the discontinuous conduction mode, and here the alpha must be greater than phase angle, where phi is the load phase angle. Phi is the load phase angle, which is given by phi is equals to tan inverse omega L by R. Omega L is the reactance of the inductor and resistance. You know the resistance and the inductor value, reactance value, depends upon that we find the phase angle. If you maintain alpha greater than phi, then we are getting these waveforms. Why especially we mention alpha greater than phi will be discussed now. So, I am discussing with the discontinuous conduction mode. So, what happens here? From alpha to pi, there was some energy must be stored in the inductor, and the energy stored in the inductor is discharges before the pi plus alpha. So, up to pi plus alpha, we have the output voltage. So, up to pi plus alpha, this portion of the negative voltage is available across the load. So, from alpha to, this is considered as the beta. That is considered as the beta. So, from alpha to beta, T1 will be in the on state. Clear? Next, from beta to pi plus alpha, the energy stored in the inductor is completely discharged. So, T1 goes to the off state and T2 is in forward bias during the negative half cycle of the source, and at omega t is equal to pi plus alpha, we provide the gate pulse to the T2. Then from pi plus alpha onwards, T2 comes to the on state and this negative portion of the source voltage is transmitted to the load. Hence why the output voltage follows from pi plus alpha to 2 pi. Output voltage simply follows the negative part of the source voltage, and current is negatively charges. And from pi plus alpha to 2 pi, there was some energy must be stored in the inductor, and that energy stored in the inductor is discharges before the 2 pi plus alpha. So, up to this instant, you have some positive portion of the output voltage. That means this portion. Why you are getting this portion? T2 is still in the on state. Hence why the small positive pulse is available across the load, and from pi plus alpha to pi plus alpha plus gamma, T2 will be in the on state. Similarly, here also you have some small part of the positive pulse due to the conduction of T2. Due to the conduction of T2, you have some small part of the positive pulse. Then if you want not to draw, this current waveform is current discharges like this. So if you want to draw the voltage across the thyristor, only this portion you are getting voltage across the T1. And similarly, reverse bias, and here so alpha to pi, T1 is in the on state. So this is the voltage across the T1, right? And here like this one, right? And from alpha to beta, T1 will be in the on state, hence why there is some voltage drop across the T1. And beta to pi plus alpha, T1 is in reverse bias, hence why the negative voltage is available across the T1. And again this negative voltage up to this, and here we have some positive pulse like this. And the output voltage waveform should be here 2 pi plus alpha onwards. Again you have the positive pulse, and again here like this. And the current waveform is positively charged, discharge 0, negatively charged, discharge 0. So corresponding this voltage like this. So here T1, T2. So up to this, and again T1 goes to the reverse biasing state like this. This is the voltage drop across the T1 or voltage across the T2, the mirror representation of this voltage. What you are getting here? Positive. So see here negative voltage now, so positive, and this one up to this, and again here positive, negative like this. So this is the voltage across the T2. So these are the output voltage and current waveforms. Output voltage, output current, and voltage across the thyristors under RL load. And especially the load phase angle is greater than phi, then only you are getting the output voltage like this. If you maintain alpha less than or equal to the load phase angle, then if alpha is less than or equal to the load phase angle, then So if alpha less than or equal to phi, if the firing angle is either equal to the load phase angle or below the load phase angle, we are unable to control the output voltage. We are unable to control the output voltage. Here phi is the load phase angle. If you consider the alpha is equals to phi, then we are getting the continuous conduction mode. So from this phi to pi plus phi, T1 will be in the convex, and pi plus phi to 2 pi plus phi, T2 will be in the on state. So output voltage and the source voltage both are same, but the current should be lags to the voltage by an angle phi. So especially for this full wave AC voltage controller under RL load, if alpha is below the phase angle or equal to the load phase angle, we are unable to control the output voltage. Whatever the source voltage is available, the source is simply available across the load. And if you want to control the output voltage, the load phase angle must be below the firing angle, or alpha is greater than the load phase angle. Then only we are able to control the voltage. Then only we are able to control the output voltage. So under this RL load, when the source is connects to the load, then what you are getting here, Vs is equals to R into I naught plus L into di naught by dt. Here Vs is nothing but Vm sin omega t is equals to R into I naught plus L into di naught by dt. Here this is the first order differential equation. So the solution of this equation simply given by the I naught is equals to Vm by Z sin omega t minus phi plus a into e power minus r by L into t. The solution of this equation, this is the first order linear differential equation. The solution of that equation is simply given by I naught is equals to Vm by Z sin omega t minus phi plus a into e power minus r by L into t, where Z is equals to root of r square plus xl square or omega L square, and phi is equals to, already we will write tan inverse omega L by r. Here this A is the constant which is determined by using the initial conditions. What are the initial conditions? From that waveform at omega t is equals to alpha, what you observe here from this waveform, at omega t is equals to alpha, what is the I naught? 0. So I naught is equals to 0. So from this t is equals to alpha by omega. Substitute these conditions in equation 1. What you will get? I naught is 0 is equals to Vm by Z sin omega t is equal to alpha by omega na. Hence by sin omega into alpha by omega minus phi plus a into e power minus r by L, t is written as alpha by omega. So by simplifying this expression, what you are getting here? A is equals to minus Vm by Z sin alpha minus phi into e power r alpha by omega L. That is the value of A. Substitute this value A in this expression. What you are getting? I naught is equals to Vm by Z sin omega t minus phi plus A is written as minus Vm by Z sin alpha minus phi e power r alpha by omega L into e power minus r by L into t. Okay. And another boundary condition, at omega t is equals to beta, also I naught is equals to 0. See here from the current waveform, at omega t is equals to beta, what is the current? I naught is 0. So substitute that boundary condition here in this equation. You substitute that boundary condition, I naught is 0. So 0 is equals to Vm by Z sin omega t minus phi na, that is sin omega t is beta by omega minus phi, sin omega t minus phi minus Vm by Z sin alpha minus phi e power, what you are having here, e power r alpha by omega L e power minus r by L into t is beta by omega. So by simplify this expression, what you will get, take Vm by Z common and gets cancelled, and finally omega cancel, sin beta minus phi is equals to sin alpha minus phi e power, take r by omega L common, alpha minus beta, e power r by omega L into alpha minus beta. So by using this expression, we are able to find out the extinction angle. And here alpha is the firing angle, gamma is the conduction angle, and beta is the extinction angle. And the relation between these three, alpha plus gamma is equals to beta, and gamma is equals to beta minus alpha. For satisfactory operation, if you want to control the output voltage of the single phase AC voltage controller, this gamma is always less than pi. If you made this gamma is equals to pi, then by default the load phase angle is equals to the firing angle. If you make gamma is equals to pi, by default alpha is equals to phi. See here, from phi to pi plus phi, T1 will be in the on state. Then what is the gamma here? 180 degrees. If you choose gamma is equals to pi, then by default the load phase angle is equals to the firing angle. Hence why, if gamma is equal to the phi or less than phi, we are unable to control the output voltage of the AC voltage controller. Whatever the source voltage is available across the thyristors, the same source voltage is available across the load. We are unable to control the output voltage under alpha is either equal or less than the load phase angle. You must maintain, if you want to control the output voltage in single phase full wave AC voltage controller, you need to maintain that alpha is greater than phi. So why we are unable to control that AC voltage controller output voltage under alpha either equal or less than the phi? That is simply explained here. Operation of single phase alpha less than or equal to the phi. So what happens here? Simply So if you choose alpha is equals to 5, then by default gamma is 180 degrees. Then what about the voltage across the thyristors? 0 to alpha, we have positive voltage on up to here, and alpha to pi, we have the positive voltage across the T1 and negative voltage here, and again positive voltage and negative voltage here, also negative voltage. Clear? Right. And if you go through the voltage across the T2, here you have the positive voltage, here you have the negative voltage, and positive voltage and negative voltage and positive voltage. So 0 to 5 and 5 to pi plus 5 or pi plus alpha, like that. So this is the voltage across the thyristors. Now I want to trigger the T1 below the load phase angle. Then what happens here? If you provide the firing angle from this instant, what is the voltage across the T1 before alpha? Negative voltage. Why? Because the T2 will be in the on state during the presence of the inductor from 0 to alpha. See here, alpha to pi plus alpha. Here T1 will be in the on state, and here T2 will be in the on state, and again T1 will be in the on state. Here T2 will be in the on state. So if you maintain alpha less than 5, what happens? Even though you reduce the firing angle below the load phase angle, the thyristor T1 is unable to comes to the on state. Why? Because before the load phase angle, T2 is in the on state. Due to the presence of the T2 on, the T1 is in reverse bias. T1 is in reverse bias. If the thyristor is in the reverse bias, we are unable to brought that SCR to the on state. Hence why after load phase angle only the T1 comes to the on state. Hence why even though you provide the gate pulse here before the load phase angle, due to the conduction of the T2, the voltage available across the T2 makes T1 in the reverse biasing mode. Hence why before the load phase angle we are unable to trigger the thyristor. Once that load phase angle should cross over, then the T1 comes to the forward biasing mode, then you provide the gate pulse, then it comes to the on state. Hence why similarly here also at pi plus alpha or after pi plus alpha you are able to trigger the T2 by providing the gate pulse IZ2. Before pi plus alpha, even though you provide the gate pulse, whatever the voltage across the T2, see here, negative. So before pi plus alpha, the voltage available across the T2 is negative voltage will be available across the T2. So T2 is continuously in the reverse biasing mode due to the conduction of T1. Hence why before the load phase angle we are unable to control the output voltage. So operation of single phase AC voltage controller with alpha less than or equal to 5 means just you draw these voltage drops across the thyristors and you explain before load phase angle we are unable to trigger the SCR. Why? Because the other SCR will be in the on state, the voltage across that SCR is appears as the negative voltage where we want to turn on that SCR, then that is in the reverse biasing mode. So we are unable to trigger the SCR. And one more important point, if the AC voltage controller is operated under RL load, this gating signal representation is also very important. Okay, whereas if you go through the resistive load, see here, which type of gating signal should be represented here with R load? This one. For the single phase full wave AC voltage controller, with R load, we represent just pulse gating. But in case of the RL load, you never consider the pulse gating. Continuous gating must be represented. Hence we see here from alpha to pi, we provide the gate pulse. Why? Because we don't know where T1 comes to the forward biasing mode. Hence why the gating signal requirement under this RL load, especially either continuous gate pulse like this, or either we use alpha to pi continuous gate pulses should be used like this, or high frequency carrier gating like this, or train of pulses. This type of gating signals are preferable for RL loads. Gating signal requirement is also very important under this RL load. The pulse gating is never used to control the output voltage of full wave AC voltage controller under RL load. This train of pulses or continuous gate pulse or high frequency gating signals can be used to control the output voltage in AC voltage controller. Okay, now. So in this class, we just discussed the operation of single phase AC voltage controller with R load and RL load, and we discussed what are the various voltage control techniques like phase angle control and on off control techniques will be discussed. Thank you.